Okay, so I guess we're on, I guess for all practical purposes, would you say chapter 5? Unless you have a question specific to chapter 4, anybody? We're talking about independence, mutually exclusive, conditional probability. And we'll start now to get into actual distributions. Different processes have different distributions, if any at all. Either they're white noise or they contain some kind of information. Remember I was talking about excrement, and the turds were actually the data that you would analyze to get an idea of what kind of animals lay in it. How do we get an idea of what the distribution is of a population? What gives us an idea of what the true distribution of the data is? Yeah, you're looking at the histograms of the sample, right? As an estimate of probably, well, this looks like it's coming from a normal distribution. In biology, a lot of stuff is with the bell curve, including IQ, which is a sliver of a measurement of a test-taking ability and pattern recognition with a certain cultural overlay on how the test is written. But anyhow, it's a small, I mean, intelligence is a complicated thing, right? IQ is a ratio between the test score and your age. Okay. Here we go. Probability distributions. You can see over here where, you see these little bar graphs over here? The bar graph? Does anybody know what they are? Do you see them on the left? That's supposed to be the degree of difficulty. And so I can kind of pick out how mean I want to get. Do you see this one here, the 5.16? If you look at over here, you see the amount of time they figured. That's one of the longest ones, I mean, to calculate this problem. So they're doing statistics on the statistics. How long it takes a student to get through it and how difficult it is. But what's a random variable? Somebody explain it to me in their own words. You want me to pick a name? You know, I didn't take roll, did I? Well, I can also use that as a roll sheet. See, if I close my eyes and go like this and just put my finger down and see whose name my finger's on, I just took that sample randomly, within reason. Okay, let's see. Manzuri, huh? Yeah, I got you. Carla. Oh, yeah, you're here. Doing better? Would anybody care to venture how you understand the random variable? I got a lot of homework here. No? It is a.
It's determined by chance, right?
Yeah. There's a chance, but the fact that we're saying there's a recurring theme, a pattern that you're trying to discover, right? But still, yet you don't know. I mean, you play bingo. If it was a crooked game, you would expect some number to come up more than others, right? If it's crooked, that is structure, and that's what you're looking for, patterns. Because once you find that, you can emphasize that and use that to forecast in the future. So a random variable is random, but I want you to distinguish from the word random, because when I wanted to take that sample and I point to see whose name I select, all right, I'm going like this. This is in order. I'm trying to generate a truly random processing thing when I go like this, see? A random variable is a variable. What's the difference between a random variable and a variable that you handle in algebra? If I have x as a variable, plus let's say 3, and I equal that to y, we, as humans, we pick values to put in. We're picking x's and out comes y's. There's no mystery in the process of which the x's are getting fed in. Yeah? As a matter of fact, if you wanted to graph it, you would do an x, a y, and a little chart, basically. It's always good to look for the intercepts. So you have 0 here, let's say 0 here, right? And y is called the what? Does anybody know what kind of variable that is? Okay, now, if I had a 3 in here, right, that's the slope 3 is not a variable. Y and X are. But we call this a dependent variable. Because it depends what we're putting in for X. Okay? You see the difference now? I got this variable that's sitting there and waiting for X's to pop into it from a process that's being generated in some kind of probability manner. Do you understand what I'm saying? And that's why they call it a variable. It is a variable, but we're not quite sure what it's going to pop out to be. And of course, we don't know what this will be till it pops out. And so we start making a histogram, of these pop-outs. And we start to see the frequency in which it's popping up. Yeah? Good. And everything on that side, and the sample space, all those little morsels that we were talking about, the parameters of this, it has a parallel samples like the average, the deviation, and it has a histogram. Those are the things we're going to use. To me, it's logical. If you have something that's unknown, how are you going to learn something about it but take a sample? Right? And then you're going to take the average and the deviation of that as an estimate of what the whole population's doing. That's not any harder than that. But to get it across so you understand what parameters are and sample statistics, right? Parameters on the population, sample statistics, are the morsels that we use to do the best prediction of these things that only God knows. All right? That's the theory. All right. Okay, now we'll go back to the problem. And these are concepts, I think, that are difficult to read and understand. Right? It's differently when I say it, but in general it is. So this is a distribution right here, the number of girls, okay, that was being born. And this distribution, I think we went over this one. This one's, right, this is a distribution. What kind of distribution would this be as opposed to a continuous or discrete? Huh? That's right, it's discrete, right? Because look at the possible values of the random variable and the outcomes that they happen, the frequency at which they're happening, yeah? We know that this to be a true distribution, this must add up to 1. And each one cannot be negative, yeah? So this is happen to know it's a discrete thing. In this case, in order to kind of get an idea of what these probabilities are and where they're coming from, this table lists the probabilities of corresponding number of girls in 3 births. Right? What is the random variable? And what are the possible values of this random variable? This is the possible outcomes, and this is the probability of which it comes out. You see that? All right, now how did they get it? Well, in this case, when we're going to learn how to counting games. There's what they call permutations and combinations. These are a kind of a help to generate how big our sample size really is, because it can be large too. So we have to count in certain ways. So let's look at this one. If I do that like that, I think I did this last time, right? I came up with boy, boy, boy is a possible combination, yeah? Do you agree? And 3 births. Yeah. What? Something? Oh, you're going like, oh, it's just involuntary motion. Okay, so then I could have boy, girl, girl, and I'm going to move the boy down the line. Girl, boy, girl. Okay, one of the questions that crosses your mind is that you can see is the girls themselves doesn't matter the position. I mean, this is different, right? But there's no such, we're not switching one girl. We're not differentiating between girls, right? So, but order matters, and so here we have, and then I'm going to run it again. Girl, boy, boy, and well, actually, let's see. Yeah, you see, I'm going to actually I could just. Before I do that, let me do the other one first. So I'm running the B down the road. And so now I'm going to have girl, girl, boy. Okay. And then I have, what now I have, this is girl, right? And so what will I need now? Well, those are 4 of them, right? I got 4 of them. So then let me do another one. So do I have a situation with girl, girl, girl? Yeah, it's possible. And then we have what? Then I'll run that. We'll get girl. I don't have a girl, boy, boy, right? Somebody say right. And then I can run the girl down the road, and I have girl, boy, yeah? And I have boy, boy, girl, yeah? And so I got like, I think that's it. Okay? Now, I had to go through that in some ways to figure out what my sample size is when I'm grouping up in threes. You would agree that the sample size is 8, yes? Of possible outcomes. So, the probability of getting no girls in this distribution is 0 girls, yes? Well, I look over here and I see how many of these are girl, 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 girl. How many of them? 1. Can somebody tell me what 1/8 is?
0.125.
Wow. Now, if you don't believe at 1/8, you should learn. Because anything that people freak out about fractions, a divided by b is nothing more than putting a in the box and dividing by b. That's all it is. People still freak out about fractions. So, 1 goes in the box, correct? Somebody say yeah. And it won't go in, yes? But it will now. Correct? I bring down a 2 and a 2. Yeah? This is some basic stuff. Guess what? How many does that go in? 2, doesn't it? And guess what that is? Right? 4. Right? 0.125. The stock market moves normally in eighths of an increment. Not sure why they use the eighths, but they do. So, if 1/8 is 0.125, what is 3/8? 0.250 plus 1.25. Yeah? So, look here. So now I got 3/8. Okay, wait a minute. What's going on here? Okay, no, that's okay. I got to count here. How many ways do we have 3 girls? 1 way out of 1/8. So we got here. Then we have, one girl. Now, when we talk about 1 girl, how many times do we have just 1 girl out of let me put it right here. Is it 3 times, yeah? 3 times 1/8. You following? This is a true probability distribution, and we used some kind of counting technique to count up the different ways we could have groups of 3. And that can grow fast. So, so we have, basically you have 3 different ways, yeah, to go in there, and 3 different ways, and 3 different ways, and 3 different ways. Okay, so the random variable x, which is the number of girls in 3 has possible values 0, 1, 2, and 3. The value of the random variable x, that when you put the p in it, you see, when you put the p, you're asking, what is the probability of x? X is this. But what is the probability of 3 girls? You understand? That's the distribution in which we draw. We might get an idea of this kind of distribution, from a sample that we take, and it gives an idea of how the population might be the same sort of thing. So it says random variable x, which in this case we're asking about the number of, what's the probability of getting 3 girls. And these are this, and the value of the random variable x, that's their numerical value. Okay? Does that kind of give you a hint? A feel? It's pretty cool. It's the way that's set up for us to analyze stuff is just, it's brilliant. It's science. And that's why when we do statistical studies, we're making some kind of assumption with a certain degree of probability, right? That's better than a random guess. So in this case, it's got 100 births. And the probability of 56 girls is equal to 0.039, right? 3.9%. This is for exactly 3 girls. And this is for 56 or more. You see the difference? Now think. You know that the sum of the whole probabilities have to add up to 1, right? So if you have any one of these, right, 1 minus that could give us the difference between the amount of below 56. Right? Okay, so let's see. The relative, okay, so let's see. Okay. It says 100 births significantly, it says, is 56 girls in 100 births significantly high number? Right off the bat, you could probably say probably not, because this is pretty close to, 50%. 50% is a random task. Except that's not really how it happens. It's like 51 to 49, but that's okay. All right, I guess, is that it? Is that too easy? Nope. Okay, another distribution. We're not seeing the shape of it now, but you could graph it, couldn't you? You could draft this as being a probability. Let's say, in other words, let's say if you wanted to graph it, right? Here are your random variable possibilities. Yeah, you've got 0, 1, 2, 3, 4, 5. Okay, and then this has to add, the highest one's going to be 1. Right? I'm doing a histogram in reverse, or a relative histogram. Remember, the frequency graph is the number of observations, but a relative frequency, we took each grouping and divided by the sample size to get a probability. So if you wanted, you could just decide, like, this first thing is 0.026, maybe it'd look like this, right? And then the next one, whatever more. You see, whatever, and then you start getting an idea of, in this case, you would see that 2 and 3 are about the same, right? They are the same. And then you start going back down again, you see? Something like that. That's what that represents, that graph represents. It says, okay, and I guess, it says, okay, so 5 males have an X-linked genetic disorder. Each one, say, have 1 child each. The random variable X is the number of children among 5 who inherited the X-linked genetic disorder. Determine whether the probability distribution is given. If a probability distribution is given, find its mean and standard deviation as a probable distribution. Say if the probability distribution is not given, identify the recommendations. So, well, we should add to see if this comes up to 1, really test to see if it adds up. And if it does, then, that's a good sign of a distribution, right? None of them are negative. So it falls into definition of allowable distributions. Now, you can see that this is not the raw data. They're giving us, right? The raw data is not here. They're giving us the probability. It's the reverse. They're giving us the probability, and I can do this histogram, but I don't really know what the actual data was before they grouped it up. So, anyway, this thing here says, yes, the table shows the probability distribution. Now, is it supposed to ask for the mean or the median or something, right? They're saying mu, but in our case, it would normally be x bar because we have things. So, so let's figure out how can we calculate the distribution. Do you remember, not the distribution, the mean, mu, which normally we'd have x bar, right, because that's from the sample, but they're saying mu. And they're going to want to calculate this too, with a deviation. Now, if I had that as squared, we'd call it variance. The only thing is whether or not the other side has a square root on it or not. Okay? Now, so how do we calculate these statistics, right, in order to do that? So there should be a way to group it. Let's see if we can do it. So there are, let's see, so it says we can crunch it. So here it is, 0.016. I'm not sure if it calculated correctly, but if I put it in correctly. And a variance, do you see this number here, 0.0, right? If you were to take the square root of that, you get this. Round to 1 decimal place if needed. Did it work? Is it a different question or the same one? Okay. Let's see. Okay. So let's go back. So let's see. So in the book, let me see what equation they're using, because I'm not sure how they calculated in how to work the stat crunch on that particular. So if we want to do the frequency table, okay, so it's saying that the mean is 1.1666 and the variance is that. Now, if I were to graph that this is supposed to be the deviation from the mean back and forth, but I'm not getting these numbers. Okay, go back over here. You have to hit the shift button in order to get this this extra one. Okay. Okay. Isn't that the same number?
It says 2.5.
Oh, up here. It's the random variable itself. I was just doing this, this column, not that one. So, on that distribution, then the average is going to be here. When we're talking about this number, right here. Okay, here, where's 2.5 hit on the scale? So this 2.5 is the average. And then we go back up again. Let's see. Here. Yeah. And then we deviate. So if we were to actually graph it out, you would, sort of like a bell curve. Then the distribution from the mean, this would be one deviation left and right of the mean. Thanks. Any questions? And then, okay. Ted is not particularly creative. He uses the pickup line. If I could rearrange the alphabet, I'd put you and I together. That's corny. I don't know if I'd go for that kind of thing. I had my own technique, but that was a little more sophisticated. This, okay, the random variable is the number of women Ted approaches. He's doing a numbers game, because eventually someone will hit. If you do it, it's called the law of numbers. The random variable x is the number of women Ted approached before encountering one who reacted positively. That's my kind of guy. Determine whether a probability distribution is given, and if I guess it doesn't add up, does it? I don't know. I mean, if you were to add it up, you can add here, just 60 and 80, right? I mean, if I were to pretend like they're units of 10, 60, 80, and then what do you have, 8? So you see you have something under 1. So it's not a distribution. You can't have a variance. I'm coming up against that hard problem. Oh, here it is. Look. Ta-da. I don't know. Okay. Use the rule of thumb to identify the values that are not significant. So we have a table, and the table shows groups of 10 births and 10 sets of parents. Random variable x represents the number of girls among 10 children. Use the range rule of thumb to determine whether one girl in 10 is a significantly low number of girls. Would you expect that to be a low number? 1 out of 10? Yeah, it could happen though with a certain probability. So use the range rule of thumb. What's range? Yeah. Yeah, it's a range. From the lowest data point to the highest. That's your range, right? So they're trying to make it like a... No, we got to use the range rule. So the maximum value of a range should be the lowest observation minus the highest. And see, that would be 10, wouldn't it? What am I doing there? probability distribution of x. The maximum value in the range. The minimum value is, okay, why is the minimum value 1.7? Oh, here's the minimum. So, well, that's the smallest y guy, right? Do you agree? Or is it? Yeah, it is the smallest, right? And what's the largest?
0.226.
Yeah, I think that's the largest. So in a range, that would be my highest and lowest y observations. And that would be, let's see, how do they go about getting that? I don't remember now. Let's see. This one here, I wonder why they don't do that. Okay. Hold on. If all else fails, you can... look at the book. I don't remember right now. There's a rule of thumb from which you would calculate the range, and there's a rule of thumb that you can use to help estimate the deviation. I'm not sure if it's worthwhile learning, but there it is. And chapter 5. What page do we have there? Okay, all right, let's start there. And that doesn't work. Okay, now let's see if we can remember now. Oh, is it? Okay. It's the same idea. It's a different distribution, though. See, we use the sampling distribution, and we'll basically get an estimate of that. But that's a different distribution. Let's go back. This is proportions. It has its own distribution. So, let's see. Oh, we're still in 6, huh? Maybe I could drop that down. Let's check it out. It'd be easier this way. Chapter 5. And we were talking about that there. How to calculate the... okay. We're not there either. The next distribution we'll be doing is called the binomial distribution. Okay. So let's go to page 195. 195. Man, I was going to go a long way, huh? I mean, it'd take me a while going a page at a time. Okay. Okay. You see what's going on? At least before, when we were trying to find out the mean, that was the frequency divided by n. Frequency times each x. Now, we had probability, right? So here's now this one in terms of probability. You see? So this is the deviation. And this is, you remember how when a sample we had x minus x bar? Now they're pretending like we know God's truth. So x minus mu squared times the probability that the random... So it would look like this. This is a counter. Do you remember this little summation? You remember? So it looks something like this. So we should have a little counter like I equals 1, 2. In this case, because we're talking about the population parameter, this is going to go all the way up to capital N. So when you write it out, it's just telling you to add this capital N times. So you'd have your first observation, right, minus whatever the mu is, and then you would look at that table. Remember we had P of X is, so that one was 0 girls, say, right? And we look at what that probability is. That gets multiplied times that, yeah? And we're not at n yet, so we have to put the next step. So it'll be x2 minus mu. These are squared, aren't they? Yeah, that's a mu. And this will be multiplied times the next random variable's probability. Plus, yeah, dot, 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 plus the final one is x is the nth term, the last, right? Minus mu squared, right? Plus the final observation of the nth, whatever the last observation number is. So that's the way you would remember ours was grouped. It wasn't given the raw data. So let's see if we can find that rule of thumb that they're talking about.
Is there an easier way to do that?
StatCrunch. Yes. It should do it for you, but you know what? What the distribution that you have has maybe 5, 6, 7, 8 points. It's not unreasonable to do it by hand. I know it's unheard of now these days, but yeah, it's working StatCrunch that will help you solve it. But if you did one by hand, it might not be bad. Here's random variables. Each one of these is a distribution, and this is the probability of the outcome of each event, right? Again, I guess I don't know, having us see if it's a probability distribution. Men with color blindness. Does that look like a probability? Because that's, it looks close, doesn't it? 50, yeah, there's 50 right there. Or is it 2? No. Okay. Well, anyway, this is the pickup line. Fun ways to flirt. They have a branch of mathematics called game theory. So it's the whole mathematics of what's the best strategy to play against an opponent to increase the chances of winning. That's what these things are, kind of, right? A brilliant mathematician who was on that movie, The Beautiful Mind. He's called, last name is Nash. He came up with a Nash something equilibrium in economics. And the Nobel Prize was given to him. They don't give it to mathematicians. And they think maybe some mathematician was messing with his wife or something. Anyway, they have their own. It's called the different thing, like a Nobel Prize, but it doesn't dare. But he was so good that his math was Nobel winning in economics. You'll see it called the Nash thing. Unfortunately, he ended up being schizophrenic and started losing his mind, and he learned to control it, but there was always these extra people in the crowd that weren't really there. And later on, not long after that, he had a son that also has a brilliant, pretty good, maybe not the same, but good, brilliant. He was already doing heavy stuff in high school, and he's a university professor down in Mexico City, and he too developed schizophrenia. Okay, what am I doing here? You might have seen the movie, Beautiful Mind. No? If you get a chance, watch it. It's really nice. The dude was, well, according to them, I'm not sure it's true. According to the movie, I think he was working as a janitor, and he just was watching the board when he was cleaning up classrooms. And it turned out he was like, I don't think he'd make a good teacher, I don't know. But it showed the first day he went to a class in calculus, he just threw the book in the garbage and started teaching. Okay. That's not what I want. We're trying to solve this one problem. I forget the rule. The range rule. Use the range rule of thumb to determine whether 4 is significantly high number of sleepwalkers. But I didn't see the range rule. Oh, that's what's coming up. It's been so long. Okay, that's the expected value. All right. These are questions, right? Okay. Oh, I might binomial distribution. Maybe I ought to look at the book. See, I want the rule of thumb, right? Let's see. So I probably look under the range. Range. Okay. Maybe it's the rule of thumb. I don't know. Are you... Anybody see it? I see range, but that's number 98. I don't think that's it. Number 98. I'm not sure if I addressed this enough. The expected value is what you expect to win off of gambling. Like you're going to have a certain degree of probability of losing, but overall you would expect to either win or not. And of course, the way the casinos are set up, your expected value overall, your gambling, is supposed to be negative. Well, a lot of people tell me how much money they won on a casino, but they don't tell me what's their total cumulative loss. In total, the cumulative loss would be your expected value. And that helps you decide whether you should even take the bet. Some people don't care anyway, it doesn't matter, but okay. So expected value is equal to each observation. Remember 0, 1, 2, 3, 4, when we're talking about number of girls, times the probability of that happening. Do you remember we had the one where it was 0.125 for no, and then we had, did we go up to 0.250? And then we went, I think, 2.375s and then back it down again. So whatever that adds up to 1, then in order to find this expected value of winning or loss, you would do this. Remember, this is summation. All that means is you take the first random variable 0 times the probability of happening, plus the next variable was 1, right? Plus times the probability of it happening. And just, right? By the way, the last one I'm showing you, I think we had to take a square root at the final end. I don't remember. Okay. So, so the expected value need not be a whole number. And expected value of the number of girls in births is 2.5. That's half of 2% and a half. Right, but that's the expected value. Okay, now here we are, finding the mean and variation, standard deviation. Let's see if they use the rule of thumb there. Okay. All right, well that's, okay, here's a probability. Here's a distribution. Here are the values of x, yeah? And here's the probability that they keep recurring at. This is the number of counts that fell in a bin divided by the total sample size. Yeah? Okay, so this is the rule, what we were looking for right here. This and this. Okay, now what they're doing is they're taking exactly what I just got through saying. So in this case, look, there's the first term of this guy. The first term, right, is 0, yes, times this, which is 0. Correct? Now we go back to our counter. We haven't finished the sample, so the sample looks like it's going to be 3. Then we add the next term. That's going to be 1 times the 0.5. You see that? And 2, yes? Now we sum those up. We see that that's a probability distribution. You see it adds a 1? Okay, now by doing this guy, what we're doing is taking these things right now and adding them up. And this is how we would calculate our variance. Do you see that squared? When you see squared, you're going to see variance. If you see this without the square, this is going to have to be square rooted. That's all the difference. And they call that deviation. Okay. And now, can we find the mean? Yes, we can do it now because we have this. What's the first observation? It's 0, right? Correct? The probability is what? This? But it doesn't matter because 0 times that is 0. Do you agree? Yeah? We weren't, what we had to do was square this. You see where we had to square each one of these? Because of this part here squared? But here we don't have to square. So what would the result be? I don't know if I get this. Okay, so like in this case, this guy would be, let me see if I can do it right. So our first observation, in the summation, the first observation is going to be 0, yeah? So this just takes 0 and multiply it times its probability, which we had to do it here too, but that difference we had to square. This is even easier. So we have not hit 3, which is our sample size or population size, right? So we have to add the next one. Well, the next one, observation, x is 1. And that is 0.5, yes? Okay? And now what's the next? We haven't hit We haven't hit 3 yet, right? So we have to keep going. True? So what goes here? What's the next number?
2.
Yeah. And what's its probability? Huh? Yeah. So we have the, over here, 0.5, 0.25. This mu is your expected value. Notice that I didn't have the raw data. That's what I was looking for, that I couldn't remember this equation. Does that help? It does? Wow, that surprises me. Let's go again. It's not too bad. It'll get better and better. Okay. When I make a mistake, it shows up as a mark. Oh, we're ready to go? Is time over? Is it? It flies when you're having fun. Okay. Now, here's the result of just the range rule of thumb. So let's take care of that business because I didn't remember it. Sometimes you don't use things for a long, long time. It says, okay, the range rule of thumb is going to be mu minus two deviations. And that's what they're calling it. So you see this putting a boundary around mu. You're going to take mu and just add 2 sigma to it. That's 2 deviations to the right and 2 deviations to the left. Okay? And now they're saying if what you're analyzing is falling from this side over or this side over, this is significantly means it's of notice, of value, and this is high. If it lands in here, we say it's not really that much difference. We'll go over that next. Oh, you want to send me an email and remind me to reset that. I'm trying to set the quizzes up. I'm not sure if it allows me so that you can retake them. I want to treat it like a homework. It's okay?
Yay.
Yay?